Welcome to our exploration of quasicrystals and magnetic order. Today, we'll dive into the fascinating world of materials that challenge our traditional understanding of structure and symmetry. Quasicrystals are unique because, unlike regular crystals, they possess a long-range structural order without simple periodic repetition. Their discovery revolutionized material science and continues to intrigue physicists and chemists alike. We'll also touch on magnetic order, another cornerstone of modern physics which helps us understand how spins organize in solids. Let's begin by uncovering what makes quasicrystals so special. Quasicrystals are materials with a long-range structural order, but they don't repeat themselves in a simple, periodic way like regular crystals. Imagine a pattern that stretches infinitely but never quite repeats itself. This unusual arrangement gives quasicrystals unique properties and makes them stand out from conventional crystals. Their atomic structure is often described as a self-similar packing of atomic clusters, which means smaller clusters mimic the arrangement of larger ones. This self-similarity is a key feature in understanding their complex structure. One of the most striking features of quasicrystals is their symmetry. Unlike regular crystals, which are limited in the types of symmetry they can have, quasicrystals display symmetries that are impossible for periodic crystals. For example, they can have five-fold symmetry, which is forbidden in traditional crystallography. Their diffraction patterns known as Bragg reflections reveal these unusual symmetries, including higher-order axes such as five-fold, three-fold, and two-fold. This discovery challenged the very definition of what a crystal could be. Story of quasicrystals began in 1984 when Dan Schechman and his team observed an electron diffraction pattern in an alloy of aluminum manganese Al. This pattern showed icosahedral symmetry, with clear five-fold, three-fold, and two-fold axes. The discovery was groundbreaking, as it provided direct evidence of a new type of structural order in solids. Schechman's work earned him the Nobel Prize in Chemistry and opened up a new field of research into materials with non-periodic order. Quasicrystals are most commonly found in aluminum alloys, such as Al-Liku, Al-Mansi, Al-PDMN, and Al-Kufi. However, researchers have discovered many other compositions, including ZnMgSc and PDUC. These alloys exhibit the unique structural properties of quasicrystals, making them valuable for both scientific study and practical applications. The diversity of quasicrystal compositions highlights their importance in materials science. A notable characteristic of quasicrystals is their high electrical and thermal resistivity. Unlike regular metals, quasicrystals do not conduct electricity or heat efficiently. This property is linked to their unique atomic arrangement, which disrupts the flow of electrons and phonons. As a result, quasicrystals are often used in applications where insulation is important, and their resistivity continues to be a subject of scientific investigation. To study quasicrystals, scientists use a technique called high-dimensional crystallography. This approach involves analyzing the structure in spaces with more than 3 dimensions, allowing researchers to understand the complex packing of atomic clusters. High-dimensional crystallography provides insights into the self-similar nature of quasicrystals and helps explain their unusual symmetry and properties. Structure of a quasicrystal can be analyzed using its Fourier components. Scientists express the density distribution ρr as a sum of density waves, which helps them understand how atoms are arranged. This mathematical approach reveals the hidden order within quasicrystals and is essential for interpreting their diffraction patterns. Fourier analysis is a powerful tool in both physics and materials science. Now that we've explored the world of quasicrystals, let's shift our focus to magnetic order. Magnetic systems are just as fascinating, with spins organizing into ordered phases that are as complex as those found in crystalline and liquid crystalline materials. Understanding magnetic order is crucial for grasping the concept of broken symmetry in physics, which has far-reaching implications in many fields. Magnetic order refers to the way spins in a material organize themselves into specific patterns. In magnetic systems, spins can align in various ways, creating ordered phases that influence the material's properties. These phases are as diverse and complex as those found in crystals, and they play a vital role in our understanding of physical phenomena such as magnetism and superconductivity. Magnetic systems have been instrumental in advancing our understanding of broken symmetry in physics. Broken symmetry occurs when a system transitions from a more symmetric state to a less symmetric one, often resulting in new physical properties. Studying magnetic order helps scientists uncover the mechanisms behind these transitions and their impact on material behavior. Magnetic order is typically found in materials where atoms or molecules have unfilled electron shells and unpaired spins. This is common in transition metals, lanthanides, and actinides. These elements have d or f electrons that are tightly bound to their nuclei, resulting in unique magnetic properties. The presence of unpaired spins is essential for the formation of magnetic order. Materials with magnetic order, the d or f electrons are tightly bound to the nuclei, which have small radii. This means there's very little overlap between neighboring atoms, making the behavior of spins highly localized. The arrangement of these electrons and spins determines the magnetic properties of the material and influences how spins interact with each other. Behavior of spins in magnetic materials is influenced by interatomic electron Coulomb repulsion and spin-orbit coupling. Coulomb repulsion refers to the force between electrons due to their charge, while spin-orbit coupling describes the interaction between an electron's spin and its motion around the nucleus. These interactions are fundamental to understanding how magnetic order arises and how it affects material properties. Summary: quasicrystals and magnetic order represent two fascinating areas of modern physics. Quasicrystals challenge our understanding of symmetry and structure, while magnetic order reveals the complexity of spin arrangements and broken symmetry. Both topics are essential for advancing material science and deepening our knowledge of the physical world. As research continues, these concepts will undoubtedly lead to new discoveries and application.